Space is not cold. It is not hot. It is something worse. On Earth, temperature feels simple. Ice burns skin at -20 degrees Celsius. Fire tears through steel at 1,500. But space breaks those rules entirely. An astronaut drifting between stars would not instantly freeze. Not because space is warm, because space is almost nothing. Interstellar space contains about 1 atom per cubic centimeter. Earth's atmosphere contains about 10 quintillion in the same volume. The difference is so extreme that the word temperature starts to lose its meaning. The average temperature of the universe is 2.725 Kelvin, minus 270.425 degrees Celsius, only 2.725 degrees above absolute zero. And yet, space can still burn you alive. Cold on Earth is simple. Heat leaves your body through conduction, direct contact between atoms, and convection, where moving air carries warmth away. Both depend on matter. Both depend on collisions. Space has almost none. Earth's atmosphere is roughly 10 quintillion times denser than interstellar space. On Earth, billions of air molecules strike your skin every second. In space, almost nothing touches you at all. No wind, no convection, no conduction. Only radiation remains. And radiation is slow, much slower. That changes everything. People imagine a human in space freezing solid in seconds. Movies show ice forming instantly across helmets. Reality is stranger and, frankly, less cinematic. A human body at rest produces about 100 watts of heat, enough to power a bright incandescent bulb. On Earth, air removes most of that energy continuously. In vacuum, the body can only shed heat through infrared radiation. That process is so slow that an exposed astronaut would likely die before freezing became the main concern. The real killer is vacuum itself. Without pressure, gases in the lungs expand violently. Moisture on the tongue and eyes begins to boil. Dissolved gases form bubbles inside tissues. Oxygen disappears from the bloodstream. Loss of consciousness arrives in about 15 seconds. Not from cold, from suffocation. And during those final seconds, body temperature would barely change. Because vacuum is not efficient at removing heat. This is the paradox. The coldest environment imaginable does not freeze you quickly, because freezing requires contact, and space has almost nothing to touch you with. We know this not just from physics, but from accidents. In 1966, inside a NASA vacuum chamber, a technician's suit depressurized. He lost consciousness in about 14 seconds. When pressure was restored after roughly 30 seconds, he regained consciousness and later reported the last thing he felt was the saliva on his tongue beginning to boil. He survived. His body temperature had not significantly dropped. The vacuum had done almost nothing to his thermal state. It had done everything else. This is also why spacecraft design is more complicated than most people assume. A vehicle in orbit isn't managing one temperature. It is managing two completely different environments at the same time. The side facing the sun absorbs intense radiation. The side in shadow radiates heat into darkness. Both happen simultaneously, separated by maybe 2 meters of metal. Engineers solve this with thermal control systems. Radiators, multi-layer insulation, heating cables, cooling loops filled with ammonia. The International Space Station alone circulates about 1,500 kilograms of ammonia through radiator panels the size of a tennis court. All of it just to manage the fact that space cannot decide what temperature it wants to be. But space can also do the opposite of freezing you. Imagine drifting near Earth in direct sunlight. No atmosphere, no clouds, no ozone layer. Just raw solar radiation hitting every square meter at 1,361 watts. More than 13 times the heat the human body produces. In shadow, an astronaut slowly loses heat. In sunlight, the body absorbs enormous energy. Thermal engineering in space is essentially managing a paradox that should not exist. Even near the sun, space itself remains mostly empty. The solar surface reaches about 5,778 Kelvin. Its core around 15 million Kelvin, 15 million degrees. And yet a spacecraft passing through nearby vacuum is not automatically cooked to those temperatures, because temperature alone does not transfer energy. Matter does. Collisions do. Without enough particles, even extreme temperatures become misleading numbers. The sun's outer atmosphere, the corona, actually reaches temperatures between 1 million and 3 million Kelvin, far hotter than the surface below it. This has puzzled scientists for decades. Heat moving away from a source and getting hotter is not what thermodynamics would suggest. The corona appears to be heated by magnetic waves moving through plasma, a mechanism still not fully understood. The sun, in other words, does not follow simple rules either. This is why space contains both the hottest and coldest places ever measured. The Boomerang Nebula, 5,000 light-years from Earth, has a temperature near 1 Kelvin, colder than the average temperature of the universe itself. The nebula forms when gas expelled from a dying star expands so rapidly that it cools below the background radiation of the cosmos. A star dies, and its death creates the coldest known place in the observable universe. Meanwhile, inside stars, matter reaches millions of Kelvin, and in laboratories on Earth, physicists have cooled atoms to less than 100 picokelvin, 1/10,000,000th of a degree above absolute zero, a temperature so low that atoms stop behaving like individual particles and begin acting as a single quantum object, a state of matter called a Bose-Einstein condensate, first created in 1995. The coldest temperature ever recorded was not in space. It was on Earth, inside a vacuum chamber the size of a filing cabinet. So what is temperature, really? Not hot, not cold. Temperature is motion, the motion of particles. The faster atoms move, the hotter something is. But space is mostly empty. No particles, no collisions, no efficient transfer of anything. A region of space can have a temperature of millions of Kelvin and still feel like nothing, because there are simply not enough particles to carry that energy anywhere. This is the truth hidden behind the vacuum. Space is not a giant freezer. It is an absence, an environment where sunlight can overheat one side of your body while the other radiates heat into darkness, where the average temperature of the universe is 2.725 Kelvin, but temperature itself becomes almost meaningless. The killer is not cold. The killer is vacuum, because humans evolved for pressure, for air, for matter, and beyond Earth, matter almost vanishes. At the edge of space, survival is no longer about warmth or cold. It is about isolation from nothing itself. This is what happens at the limit.